So, how do you solve some of the world's absolute toughest problems? You might think the answer lies in a supercomputer, right? Well, what if I told you it actually comes from the fire and anvil of an ancient blacksmith? Yeah, you heard me. This is the wild, brilliant idea behind an algorithm called simulated anneal.
That's not a joke, seriously. The secret to optimizing all sorts of crazy stuff, think airline schedules, circuit board layouts, you name it, is literally hidden in the old-school techniques of a blacksmith. It sounds, well, a little nuts, I know, but stick with me here, because it's a fantastic metaphor for an incredibly clever idea.
All right, so let's start at the forge. Before we get into the code, we really need to get our heads around the physical process that gives this whole algorithm its name and its logic. It all boils down to making something stronger by, you guessed it, heating it up and then cooling it down in a very specific way.
Okay, so in the world of metalworking, this is a real thing called annealing. You take a piece of metal, right, and it's usually full of all these tiny imperfections and internal stresses. You run it through this process, and the whole point, the big goal, is to get it into its most stable, most perfect state. We're talking about a low-energy structure, which is what makes it super tough and durable.
So here's the play-by-play. First, you heat that metal up, like way up. This just floods the system with energy, and all the atoms inside start jiggling and bouncing around like crazy. They're just exploring all kinds of new configurations. Then, and listen, this is the most important part, you cool it down, slowly, super slowly. This gives all those chaotic atoms the time they need to find their perfect little spots to lock into a strong, organized structure. And boom, the system settles into that ideal low-energy state we've been talking about. Okay, that's cool and all, but what on earth does this have to do with a computer problem? Fair question. Let's step away from the forge for a second and start building that bridge from metal to math. This is where the whole analogy just clicks into place. Here we go. This is the Rosetta Stone for this whole thing. Think of it like this. A possible solution to our problem? That's just like the physical state of the metal. How good is that solution? We measure that with something called a cost function, which is our stand-in for energy. And just like in physics, lower cost is better, right? It's more stable. And the blacksmith's most powerful tool, temperature? Well, for us, that becomes a control knob, a parameter we can dial up or down to guide our search for that perfect, frozen final solution.
Okay, so we've got the analogy down. Now let's get into the nitty-gritty, the actual rules of the game. How does our little digital blacksmith actually find the best possible answer when there are like a billion different options?
You'll see the process is almost exactly like the forge. We kick things off with a totally random solution and a really high temperature. Then we make a tiny random change to it. We find a neighbor solution. Now here's the crucial step, the decision point. Do we keep this new solution? I mean, if it's better, duh, of course we keep it. But the real magic, the secret sauce, is what happens when the new solution is actually worse. And all the while, we're slowly cooling the system, getting pickier and pickier until we finally freeze on what we hope is a fantastic answer. And that question right there, that brings us to the absolute heart of why this algorithm is so frickin' clever. Think about it. Most algorithms are greedy. They always move towards a better solution. So why in the world would you ever program something to sometimes accept a move that makes things worse? It feels totally wrong, right? Completely counterintuitive. The answer is actually pretty simple, but it's incredibly powerful. You do it to escape a trap. See, a lot of complex problems are full of what we call local optima. These are solutions that look pretty good, but they aren't the best overall. A simpler algorithm is like a hiker in the fog. It'll climb the first hill it finds, get to the top, and then just get stuck. It has no idea there's a giant mountain right next door. By being willing to accept a worse move, by taking a step downhill on purpose, simulated annealing gives itself the freedom to wander around and explore the entire landscape to find that much higher peak.
Now, that whole ability to take a step backward, that's all controlled by our temperature knob. But how you turn that knob down, the cooling schedule as it's called, is basically an art form. And honestly, it's probably the most critical part of this whole entire process.
This really is the fundamental trade-off. Back in the forge, if you take red-hot metal and plunge it into cold water, you're cooling it way too fast. You trap all those imperfections inside and you get a weak, brittle result. But on the other hand, if you take, a week to let it cool, that's just not practical. It's the exact same idea here. Cool down too quickly and you'll probably get a junk answer. Cool down too slowly, well, you might be waiting until next Tuesday for a result. The real art is in finding that perfect, just right schedule.
So one popular strategy is called exponential cooling. I like to think of this as the impatient one. Imagine at every single step, you just cut the temperature by a fixed percentage, like say 10%. What this means is the temperature plummets really fast at the beginning, when it's hot, and then the drops get smaller and smaller later on. It's a pretty fast and often pretty effective way to go, trying to strike a nice balance between exploring and eventually settling down.
And then on the other end of the spectrum, you've got logarithmic cooling. This is the patient, perfectionist. With this one, the temperature drops agonizingly, slowly, especially as time goes on. This gives the algorithm a ton of time to explore every single nook and cranny of the problem space. For those really hairy problems, the ones with traps everywhere, this slow, methodical approach is sometimes the only way you're ever going to find the absolute best solution.
And of course, there are other flavors too. Linear cooling just subtracts a fixed amount each step. It's a nice, steady, moderate pace. Quadratic is kind of cool. It starts off fast and then slows way down, which is great for doing some fine-tuning at the very end. But look, at the end of the day, there is no single best schedule. It's just like a real blacksmith. You have to pick the right technique for the specific job you're working on.
All right, enough theory. Let's make this real. We're going to apply our new blacksmithing skills to one of the most famous, most notorious optimization puzzles out there, the traveling salesman problem.
So the goal sounds super simple, right? A salesman has to visit a bunch of cities. The question is, what's the absolute shortest path that visits every single city just once and then returns home? Sounds easy, but it's deceptively hard. As soon as you add more than a handful of cities, the number of possible routes just explodes into these astronomical, mind-boggling numbers.
Okay, so imagine a simple, greedy algorithm tries to solve this. Its strategy is simple. Always go to the nearest unvisited city. It might spit out a path like this one, with the total cost of, say, 34. And you know what? It looks okay. But it's trapped. It's in one of those local optima we talked about. From this position, any small change, like swapping two cities, actually makes the path longer. So the greedy algorithm just gives up. It thinks it's done, that it's found the best solution.
But now, in comes our hero, simulated annealing. Its temperature is still pretty high, so it has a lot of energy. It tries that same swap of two cities. Now, this new path, it might actually be a little bit longer. It's a worse solution. But because the system is still hot, the algorithm says, you know what? I'll take it. It accepts the bad move. It takes one strategic step backward, so that it can eventually find a path to leap forward. And this is the payoff, right here. By escaping that little trap, it's now free to explore a whole different part of the solution space. And look what it finds, a much, much shorter path with a total distance of 28. It found the globally optimal solution, all because it was brave enough to make a temporary sacrifice. So, what's the big takeaway here? After our journey from the blacksmith's forge all the way to a complex algorithm, what have we learned? Let's wrap this up by looking at the good, the bad, and the ugly of this really powerful technique.
So, what's the final verdict? Well, its biggest strength, its superpower, is its genius ability to escape those local traps that leave simpler algorithms stuck in the mud. But it's no magic bullet. The whole process is pretty sensitive. You've got to really carefully tune all the knobs and dials, especially that cooling schedule. And the price you pay for finding a near-perfect solution can sometimes be a really, really long wait time.
And that kind of leaves us with this one final thought, doesn't it? Simulated annealing teaches us a lesson that's actually way bigger than just computer science. It teaches us that sometimes to find the absolute best way forward, you first have to be willing to take a strategic step back. So the question to leave you with is this: when is making a wrong move the absolute right one to make?